Hello, everybody, and welcome to Team Jeopardy's final design review. For our Capstone design project, we created an autonomous soil core sampling robot. Let's begin. We begin with our problem statement. For those unfamiliar, soil core sampling is the act of collecting cylindrical soil profiles from the earth. Currently, this is an incredibly tedious and time-consuming process due to the difficult nature of extracting the marshland soil. So our design aimed to significantly reduce the time and human labor associated with collecting these samples. And we believe that this device can increase the accessibility and utility of soil core samples and extend their use into many new industries. Next slide, please. There are a few things to focus on from our problem statement. So first of all, soil core sampling is a very hard and very inexact process. We learned this from field testing. We learned exactly how difficult driving lengths of PVC pipe into the wetland soil is and couldn't imagine doing it all day. At the same time, field testers are expected to maintain a degree of quality that simply isn't attainable with hand tools. Our technology has fallen behind our scientific needs, and it's time that we caught up. And so in order to resolve these issues, we designed Autocore. Autocore replaces as much of the human labor associated with soil core sampling as possible. The process went from forcing metal tools into the ground to setting our device in place and just pressing go. Since these samples are often used to check the contents of soil in marshland and wetland environments, we limited the scope of our environment as such. Next slide, please. We got our inspiration from one of our group members who had an internship collecting marshland soil core samples with Professor Engelhardt, an expert in the field. Our group members spent a great deal of the summer toiling away in the marsh, extracting and collecting these samples, and they got to see for themselves how inexact of a science it was and how much it could be improved upon. There are a great deal of potential research opportunities for many different stakeholders that would value this geological information, including groups interested in conservation, wetland real estate development, oil and natural gas mining, scientific research, and civil groups like the USGS would all hold great interest in investing in our technology. Since our field is incredibly novel, next slide, please. Since our field is incredibly novel, our only existing competition comes from manual and hand tools. The image on top shows the blade of a hand coring tool, and that part is the part that's actually forced into the ground. This is typically attached to a longer pole that allows for a little bit easier use, and that can be seen in the image below. Sometimes mechanical augers can be used for similar purposes, but ultimately disturb the soil far too much to collect accurate and scientifically valid soil core samples. Evidently, our market is wide open and perfectly set for Autocore to succeed.
This is our weighted objectives chart, where we organize our priorities upon the first conceptualize this device and brainstorm our ideas to understand what would make this device a compelling product. The key points to take away from this figure is that being a soil coring tool that is going to replace traditional augers, the majority of our criteria focuses on the actual soil coring process, shown in blue, such as the sample quality, consistency across samples, sampling speed, and overall ease of use. The second largest section, shown in red, focuses on the financial feasibility of this product to make sure that this product is as realistic as possible, such that it can become an actual product on sale. Thus, many of our design decisions were driven based on the balance between how much we can make the sampling process better while making it as simple and affordable for any user.
So for our final design metrics, there's a closely related to our weighted objectives. We have a few categories that we'd like to achieve specifically. So in terms of speed, we'd like to have somewhere around 60 samples per hour. Definitely at least more than the average samples per hour of the traditional auger. Sample size accuracy, we'd like to achieve greater than 95% to make sure our quality is good. Low soil disturbance, constant velocity control is the method that we want to use to achieve this. Basically anything that avoids significant jumps in force or speed when taking the sample. Path planning, we want to accommodate at least 200 nodes or so with our pathfinding algorithm. And price, we'd like to keep it at about 5,000 to keep it competitive with the price of the traditional auger. Lightweight, the weight is very important to us because this is something that the user is going to have to lug around to each individual node. And operators, about 3 is the maximum, absolute maximum that we wanted. So we would like to have it be recommended to And battery life, 4 hours is a good lifetime that we wanted for our battery for decent usage in terms of the field. Next slide.
All right, let's start with the first subsystem. That's the coring head. This is the part of the tool that's going to actually go into the dirt. We deliberated on how to best implement the dirt collection itself. And there would be a lot of complication if we had one single tool that we use, because we would have to automate cleaning off the tool or ask the user to do that in between every sample, and that can get very messy. So instead, we decided to go with interchangeable PVC pipe method. This is a section view of the coring head as we currently have it. As you can see at the bottom right, that's the PVC pipe that would be used. It would be plunged into the ground, the dirt would be contained in there, and then the user would just change out the pipe, using that pipe as sample storage and then just put in a fresh one. There's a valve system you can see on the top left that'll let the air out of the pipe as it's being pushed into the dirt. And it'll also double up as creating a vacuum seal to help hold the pipe in place as it's being pulled back out. Additionally, we have a way to release the pressure to allow the user to change the pipe out easily. Next slide, please. As you can see here, the pin we show over here on the top, that when that's pushed up, this valve is opened, and that's how the user will change out the pipe. This is the coring head in the main assembly itself. Next slide, please. And finally, here's just a quick exploded view of all the parts inside. It's very assemblable and also not very difficult to manufacture. Next slide, please.
So now we're going to go over the actuation subsystem. Next slide, please. First, we're going to start with a design. So the actuation unit consists of, or it's designed based off a 2-degree of freedom system. The linear degree of freedom is needed to push the coring tool into the ground and retrieve the sample. And the motion is generated using the ball screw, and the linear motion is then translated to the drill head using a bracket piece. The ball screw was determined to be the best method for the linear actuation due to its precision and accuracy in positioning, which is necessary to have high quality and repeatable sample sizes. A guide rail and slider are attached to the bracket to ensure that there is no significant deviation from the linear motion during coring. For the rotational degree of freedom, the motion is translated to the drill head using a shaft independent of the linear motion. The primary purpose of this degree is to supplement the linear coring motion and to reduce soil disturbance. And there is an animation that you can play that will show those 2 degrees of freedom in action. We also chose to use DC motors so that we could implement PID control to achieve constant velocity, which reduces soil disturbance and increases the quality of the sample. This design for the actuation unit guarantees a linear and radial sample size accuracy above 95%, and the components were sized so that the speed of sampling is 30 seconds and the experimental coring force requirements is met. Next slide, please. So now we're going to look at the component selection. So the linear degree of freedom requirements were calculated by finding the required drive torque for the ball screw, and the speed was found using the desired linear velocity and pitch of the ball screw. And you can see that those requirements were 488 RPM and about 0.18 Newton meters. And we found a motor off of Robot Shop that satisfied these requirements with a factor of safety of almost 3. And it also includes an encoder. For the rotational degree of freedom requirements, we found the requirements using the inertia of the PVC pipe and by setting a maximum speed of 100 RPM. So the resulting torque that is required is about 0.014 Newton meters. Since we're unable to estimate frictional torque generated by the contact between the pipe and the soil, a high factor of safety was desirable for this motor. So we chose the motor you see on the screen from Robot Shop. It has a really high factor of safety, which is good for our purposes. And we also chose the ball screw mainly off of the sample size that we want, which is 1/2 foot long. And that was the primary metric that we used to choose the ball screw. Next slide, please. So next we wanted to verify the performance of this actuation unit. And the first thing we wanted to look at was whether the device would be able to core without experiencing failure under the expected coring loads. And to verify this, we performed a static FEA on the bracket and connection piece in the actuation unit, which is the point that is most likely to fail during operation because the linear force applied by the ball screw is focused on this area. The results demonstrate that the components are able to withstand the maximum coring forces with a factor of safety of 2 without yielding. Next slide, please. So next we wanted to test whether the device would be able to collect samples with a high sample size accuracy, above 95%. So the transverse vibrations are really the primary concern during drilling operations, as they can enlarge the hole that is being created, which we do not want for our application, as it would cause disturbances in the soil and decrease the sample quality. So we estimate transverse frequency to be under 1 Hertz with a maximum amplitude of about 0.024 millimeters. And for the nominal PVC pipe diameter of 1.25 inches, the maximum error due to these transverse vibrations is about 0.066%, which is well within the specifications of 95% accuracy. We then considered the rotational vibrations due to the rotation of the motors, and we found that they are under 9 Hertz, which is relatively low. And considering that natural damping will be coming from the environment, we consider that these vibrations are pretty negligible and will minimally affect the quality of the sample. Next slide, please. So finally, we wanted to check that the device can core in various types of marshland soils. And based on feedback from Professor Veronica Santos, who works with granular media, we determined that we could model the soil as a solid body with specific properties to mimic soil. And we determined these specific properties by using the rule of mixtures and assuming that a soil sample would be about half water and half soil. So by applying these material properties to the solid body, we determined the amount of force that a coring tool would need to take a sample. For a soft and loose soil sample would be 37 newtons of force, and for a compact soil sample, 70 newtons would be required. Since our design was initially based off the experimentally determined coring force of 100 newtons with a factor of safety of 2.8, we concluded that our device is capable of coring in various soil types that are typically present in marshland. Next slide, please.
So on screen, you can see our final chassis design with all parts included. And we yielded this from a design process that included various rectangular and cylindrical frames, but we ultimately landed on our optimized system seen below. We optimized our chassis for maximizing strength, and we're still on the previous slide. We optimized our chassis for maximizing strength and minimizing weight. And while many of our initial designs used aluminum 6061 alloys, our material, we continually face issues with the inability to reduce weight further. So in order to meet our weight optimization goals, we changed our material to ABS plastic, which will be manufactured using injection molding procedures. And ABS plastic is a sturdy thermoplastic that is resistant to environmental wear from abrasion and corrosion that also meets our strength requirements. Next slide, please. To begin, we can see our actual chassis frame, which is cylindrical and contains several openings for our internal systems to be mounted. On top of our device, you can see the mounting points for our gimbal system to attach to the chassis, and additionally, mounting points for our GPS unit, access door, and strap mounts can be seen on the external surfaces of the device. The bottom of our device is filled apart from the hole at which our PVC pipe exits the system in order to prevent water and environmental damage to our internal electronic parts. Next slide, please. So here we have our GPS unit subassembly. It's composed of several parts, including the display support, the screen, top cover, device power switch, and the appropriate fasteners for securing each component together. The top display cover and support are both composed of ABS plastic as well. Due to the thinness of our chassis, we decided that using a plastic weld would be more effective than securing the GPS unit via fasteners. This eliminated the possibility of fatigue-related cracking and failure at fastening points. ABS plastic is able to be welded chemically without reducing the overall strength of the material. Next slide, please. So here we see our door, hinge, and latch mechanism that enables users access to our internal components of our drilling mechanism and allows them to collect samples once they've been extracted from the ground. Our latch prevents any chance of the door opening during drill operation, keeping users safe and clean at all times. Next slide, please. Our chassis has several other features, including footholds that allow the users to offer additional support to the device stability if necessary. And these are seen in the image on the left on either side of the device. In the same image, you can also see one of our strap mounts And these are screwed into our chassis and allow users to easily carry our device from sampling location to location by simply strapping the device over their shoulder. Lastly, while the gimbal system innately has our system resting as nearly perpendicular to the ground below, in order to ensure users are getting the best sample quality possible, we have included a circular bubble level that sits on top of the device seen in the image on the right. Users will now be able to visually confirm that their device is as vertical as possible to obtain the perfect soil profile.
Okay, so for our leveling stability mechanism, we decided to go with the tripod shape to stabilize on uneven surfaces. And pegs were attached at the end of the legs for better stability in mud and dirt. And the gimbal is to be attached below the tripod head in order to orient the chassis using gravity. As you can see in the picture, when the tripod is deployed, the brace ring in the middle is at the bottom. Its position is locked by slotting the tripod pin into one of the holes so that it doesn't move up or down. The legs are at 30 degrees from the vertical, and when the legs are folded, the braces will go up, the brace ring in the middle will go up, and you can also move the tripod pin to the upper hole to lock it in place in that folded position. Aluminum's 6061 alloy was used as material in order to have lightweight, since we do want this machine to be portable. Next slide, please. For the bearing joints, we decided to separate them into multiple parts in order to facilitate assembly and increase manufacturability and decrease manufacturing cost. This, of course, required more fasteners in place, and we decided to use 2 for each interface in order to prevent any unwanted rotation from happening. Most fasteners used here are nut symbols ranging from 3 millimeter to 10 millimeter diameter. For all parts, there's at least a factor of safety of 2.5. And for the bottom left picture, that's the leg. You can see one fastener in the middle. There's another one at the bottom that's blocked by the bearing joint, but those are supposed to represent rivets. Because they're fastening into the leg that the opposite side of the interface is really difficult to reach, we decided to use rivets for those specific interfaces. And we also made grooves for retaining rings to take in place at the bearing joints so that the bearings wouldn't miss position. And we also added bearing caps in order to prevent any dirt or water from going into the bearing and breaking them. And on the right, that's the exploded view of the tripod system, except the redundant parts are removed in order for the diagram to be more simple. Next slide.
All right, let's talk about the next subsystem, which is the gimbal. This is going to be the interface between the legs and the chassis subsystems that we just looked at. Our original idea for having perpendicular samples was to have actuated legs, but that ended up being a lot more complicated than we would have time to make. So instead, we went with this. It's a gimbal. It'll use gravity to make sure the chassis is directly perpendicular with the ground, and that's a lot more reliable. The 2 main forces that the gimbal has to withstand are gravity from the weight of the chassis itself, and also there will be a sideways lateral force from the 2 pins you see over here. So the idea is that it's normally freely rotating. So when the user sets up the machine, it will automatically level itself and make sure that the chassis is perpendicular. And then after that, the user will use the cam levers you see there to lock it in place and make sure that nothing will move as coring actually begins. We also added some handles there to make sure it's easy to get leverage. And on the right, you see a static analysis of all those forces applied. And this has a factor of safety of 10, which is kind of high, but since it's a very high load bearing position, we felt it would be necessary to have this be very safe. Next slide, please. And this is just an exploded view showing how all the pieces will line up and be assembled. That's it. Next slide, please.
Okay, so I'll talk about the navigation system. So one of the main objectives of the device was to increase the overall productivity of the user by shortening the time it takes to collect each soil core sample. And so the sampling procedure consists of two main phases, the drilling phase and the relocation phase in between samples. And the drilling phase is optimized by the mechanical design and the motor controller, while the main goal for the navigation system was to enable the user to follow simple commands that maximize their efficiency during the relocation phase. And fundamentally, when looking at the basic steps in the soil core sampling procedure, this problem can be classified as a traveling salesman problem, a TSP, a well-known NP hard problem that is infamous for not having a single efficient algorithm that is good at looking for an optimal solution. So, and in addition to being a TSP, the problem is inherently non-Euclidean due to the person accumulating more sample cores along the way, changing the effort it takes for an individual to travel a set distance. So, based on preliminary research done at the beginning of the quarter, we found that there's several approaches to approximating the TSP by dividing up the entire sample set into smaller groupings and running a TSP solver on each group so that the complexity is significantly reduced with little trade-offs on the actual quality of the generated trajectories. And this method actually also helped model the action of returning back to the starting location in order to drop off the collected sample in a single location. So this actually ended up helping us. And so for the clustering algorithm, we decided to use the same size k-means that is based off of the basic k-means, where a cluster representative is elected from an average of all nodes classified in that particular cluster and uses that representative to reassign nearby nodes in the next iteration. The special feature of this same size k-means is its ability to control the number of nodes in each cluster by swapping cluster IDs with another node and constantly keeping the total cluster capacity count the same throughout the entire simulation. All of these figures shown in this down here shows the clustering algorithm working for various types of sets, sample sets and clustering capacities, showing that it basically works regardless of any type of input we give it. And for the TSP solving algorithm, we decided to use the ant colony optimization algorithm, which mimics the behavior of ant colonies looking for a path to nearby food sources. The algorithm relies on simulating thousands of ant colonies or ant agents who stochastically selects their new destination based on two heuristics, relative distance to the next node and the pheromone traces left over from previous generations of ants. And once an ant makes an entire path, that path is then evaluated based on required effort and leaves a pheromone trace that reflects that evaluation for future ants to reference. And by basically running this across multiple generations, the algorithm is able to come up with an efficient path that the ants took without searching for the entire permutation of all trajectories possible. The efficacy of the algorithms shown here, with the score gradually improving the score over the number of iterations that we ran this simulation for. And it also matches the results that we got from our brute force method while testing it using a smaller sample set. So we're confident that our implementation of the TSP is working. And, oh, sorry. And despite not being able to do the actual field test to show that the advantage of using this navigation system, these individual results and knowledge of the non-Euclidean nature of this problem at hand makes us confident in our system being capable of generating an efficient path for the user to follow.
So going over to the motor control subsystem, sorry, I think we had our slide slightly misordered there. So for our, as we mentioned before, the Autocore is a highly novel problem that there hasn't been a whole lot of other competitors or research or anything done in terms of automated core sampling. So we had to do a lot of work into researching alternate fields and what's the best methodology for taking samples. And there isn't a whole lot of work that has been done on that in terms of how to best take a sample with the least amount of disturbance, and what's the best way of drilling efficiently and with the greatest amount of speed, and intelligence in terms of how an algorithm can best approach that. So originally we had planned to use some sort of Markov decision process model for our controller, but we realized that for our problem, we didn't really need to have so complex of a model, and because there wasn't that much dimensionability in terms of control that we had over our output. So we went with a PID controller, and you can see this block diagram that we have for our PID controller. It's more specifically a PI controller because we determined that the D component was not necessary for our model. And we initially had a relatively simplistic implementation, but upon further evaluation and feedback that we got, we eventually included more aspects to the sophistication of our simulation. Next slide. So our PID controller, we implemented the model of lateral earth pressure, and also the, as we've seen before in earlier slides mentioning the ball screw, we simulated the forces generated by those, both the output of the ball screw and the detrimental effects of lateral earth pressure in the soil, and as well as friction. And the ball screw thrust force is something that we've calculated with equations from the MAE side. So we use those results to help model, change our model for the PID controller, and you can see that the constants we generated. The sampling time is around 7 to 10 seconds on average, and this is well within the range that we wanted for our samples per hour. And also we can see that the error in terms of keeping the velocity constant is also within reasonable specifications that we have for minimal disturbance, which is one of our metrics that we wanted to shoot for. Next slide. So another interface that we're going to talk about is the subsystem is the user interface. Next slide. So the user interface, we mentioned before that there was a screen that would be mounted on the device. And so that is going to house a user interface that the user will use to access the navigation system. And you can see here on the left is the general overview of the GUI that we have. The settings are mostly on the left, and you can see some sliders on the right. These are all things that the user can set in terms of node selection, field size, number of samples that you want to carry maximum on a trip, total number of samples. If you're picking the samples yourself, you can change the minimum distance between generated samples if you want to use the random generation method. Also, the echo weight penalty plays into our weight formula, which I'll talk a little bit more about later. But the main way the user interacts with this, the first step they would do is either use node selection to generate nodes manually. You select them with the touchscreen, or the random node generation, which is implemented via the Poisson disk sampling. And so next slide. You can see that once you've generated the samples you want, you pick what's called a home base, which is basically a single node that all the clusters link back to. It's essentially the point. Each cluster is like a trip where you carry all the samples with you, and once you get back to your home base, you drop them all off. So after selecting a home base and clicking the solve button, we perform the earlier mentioned k-means clustering and the echo algorithm to the nodes, and we'll generate a result something like this. On the left, you can see the overall output of all of the clusters overlaid in different colors. And on the right, you can see the individual plots for each cluster. On the right is the arrows that are color-coded, that they show the path, the order you would take, as well as the color indicating how much weight you'd be carrying. The lighter green indicates that you have fewer number of samples carrying, and then towards the end of it, that's the highest number of samples you're carrying, obviously, because that's toward the end of your trip. And this plays into our weight formula, which is basically the graph that we feed our ACO algorithm. We have a set of nodes, which are vertices and edges. Each of the edges, we set some sort of weight. And earlier we were using just pure Euclidean distance for this, but we changed our methodology to have a more complex weighting formula that considers both the amount of distance you're traveling and also the weight of the number of samples you're traveling. So that is one aspect that the user can control the weighting of from the settings. Next slide. And so you can see from this GIF, the last feature is sort of a user guidance method where basically you can go through each node individually and you can, it will animate and show you that red star is going through and visiting each of the nodes. And basically this is a way to guide you through your path. You can see the distance to the next node and the heading. This will animate through every cluster one by one. And this is basically what you'd use while you're going about. Another thing to mention is that all of the interface that you've seen so far is compatible with touchscreen in the sense that you don't need a keyboard. It's all just buttons and spin boxes and sliders. So it was designed with that in mind. Next slide.
Yeah, so I'll be going over the electronics that we'd picked. So that would be the next subsystem. So the next slide, please. Yeah, so for powering the device, we decided to go with 12-volt batteries. Specifically, we'd be using two 12-volt batteries, and we would be wiring them in parallel. That would be in order to increase the overall capacity. So one battery alone would be 6.8 amp hours, but two batteries would be 13.6 amp hours total. This would be the VIDAR 12-volt high-capacity lithium-ion battery. So we chose a rechargeable battery so that the user could easily recharge the battery before or after soil coring. We also made sure that the battery came with the JFC connection for easy connectability. And given that we're using two batteries, we calculated that the overall system should last around 4 hours for continuous operation, meaning the screen is on, the motors are on, and the Raspberry Pi is on. Next slide, please. Yeah, so for the power switch, we just chose a simple single pole double throw switch, meaning you can switch between on mode and then off/recharge mode, which would link to the port that you would connect to. Next slide, please. So for the microprocessor, we're using a Raspberry Pi 0W, which is the most basic version of the Raspberry Pi that we could find. And the Raspberry Pi outputs 3.3 volts to power the sensors and the screen, and obviously it controls things like the motors. Interfaces with motors. Next, we chose to use a GPS IMU in order to tell where exactly the user was during navigation, and also so that we could tag what location each soil sample was taken from. So we needed to make sure that the GPS had a high enough horizontal position accuracy. So we found this GPS IMU with a horizontal position accuracy of 2.5 meters CEP, meaning circular air probable. So 50% of the time you're going to be within 2.5 meters. And also keep in mind that accuracy will largely depend on the weather that you're sampling within. So if it's a really cloudy day, for example, accuracy would be worse than if it was a really sunny and clear, bright day. Next slide, please. So for the screen, we chose to use a low power 800 by 480 pixel TFT screen. So that's just for displaying the navigation and guiding the user to the next sampling location. Next slide, please. For the control of the motors, we decided to use the Thunderbird motor controller, which outputs 5 volts to power things like the Raspberry Pi. And then it also outputs 12 volts, which we use to power each motor in the system. So that would be the rotational motor and the linear motor. Next slide. So in order to measure the amount of current going through the linear motor, we decided to use a current sensor. So this way we could detect when the motor starts to need more current, which would indicate when the system had reached contact with the ground. And the current sensor outputs a voltage signal corresponding to how much current is flowing through it. So next slide, please. Because of this, we would need to use an analog to digital converter because the Raspberry Pi only reads digital input. So we would need to convert from the analog signal achieved from the current sensor and then transmit that to the Raspberry Pi. Next slide, please. In order to determine both the height at which we accord the samples relative to one another, and also the absolute height relative to sea level, we decided to use an altimeter with, or based on pressure of where you're coring. So this altimeter has 1 meter accuracy with up to 0.02 centimeters precision, and also we would be using that to tag the height at which each sample was obtained. Next slide, please. And then this is just a connector that we use to connect the GPS IMU to the Raspberry Pi. Next slide, please. And here are some more connectors. The male JST connector is for connecting the external powering port to the batteries through the chassis, and then the 12-volt adapter makes it easy for the user to recharge their battery. Next slide, please. And so they would use that 12-volt adapter through this barrel jack connector into a JST connection. And the JST Y splitter is what would link the batteries in parallel in order to create a larger capacity battery. Next slide, please. And here's a schematic of the overall system. So you can see the different connections with the JST, the batteries in parallel, the motor controller, the motors, the analog to digital converter with the current sensor, and the Raspberry Pi, which is interfacing with the screen, the altimeter, and the GPS IMU.
In conclusion, the Autocore is very successful at all the tasks that we set out to do. We greatly improved sample quality, the speed of how many samples we can take, the consistency from sample to sample, and finally, ease of sampling. The product has great battery life so that in one battery cycle, it's possible to take many more samples than you'd be able to in a whole day of traditional coring. And while the cost remains very high compared to a manual tool, the system will still pay many dividends very quickly just based on labor costs alone. We have 15 times the throughput of a traditional auger with much less manpower required, making the cost fairly reasonable for any team that takes soil samples on a regular basis. Over time, this product will save substantial amounts of time and money, opening up the possibility of smaller organizations and private researchers to use Autocore for their own purposes. With industries like real estate development, conservation, oil and natural gas production being more profitable than ever, Autocore is in the perfect spot to become a centerpiece of multiple industries. Thank you for listening to our presentation.